Good afternoon. Can everyone hear me okay in the back? Okay. On behalf of Division 35, Greg Davis and I would like to welcome all of you to this special seminar. My name is Ken Urquiza, and I am in the Thermal and Cryogenic Engineering Group. I came to JPL actually just a year ago, so I'm still relatively new. But I'm very interested in this. My dissertation was on a very similar topic. It's on heat transfer nuclear reactors, so very relevant. And I think that when discussing nuclear power, it's always helpful to provide a little bit of context. You know, the word nuclear frightens a lot of people, particularly because it's often mentioned in the context of weapons or explosions. Fortunately, catastrophes at nuclear power plants are very rare. And at most of our nuclear power plants in any given year don't make the news at all. And in the U.S., nuclear power is a big part of our energy portfolio. Although half of our energy, or our electricity, comes from coal, nationally, our 104 nuclear reactors currently provide 20% of our electricity. And the U.S. produces more nuclear energy than any other country in the world. Now, because I know most of us are very interested in climate change and issues related to energy and the environment, I'd like to point out that 75% of our non-CO2 emitting electric generation comes from nuclear power. I just want to repeat that 75% of our non-fossil electricity comes from nuclear power. The other 25%, by the way, is mostly hydroelectric. The point is that nuclear power plays a big role, or you could say is a key technology in mitigating climate change. So, onto the topic at hand. Last month in Japan, a violent magnitude 9 earthquake and tsunami took more than 10,000 lives. The events created serious problems at two of Japan's nuclear power plants, Fukushima Dai-Ichi and Fukushima Dai-Ichi. To discuss these events, our speaker today is Dr. Joseph Shepard. He's the C.L. Johnson Professor of Mechanical Engineering and Aeronautics at Caltech, where he's also the Dean of Graduate Studies. So clearly he's very accomplished. The question is, what does he know about nuclear power plants? I looked into it. Fortunately, he does know quite a lot. You'll find that if you look at his CV in the publication list, he has publications in the American Nuclear Society, in the Journal of Nuclear Materials, dealing precisely with nuclear systems and topics that are highly relevant to this crisis, such as hydrogen explosions, detonation, multi-phase flow, accident progression in nuclear power plants, and pressure vessel integrity. Today he will discuss the design of the boiling water reactors at Fukushima Dai-Ichi and discuss the events that led up to the crisis from a reactor design and safety analysis perspective. He will also take questions. So please join me in welcoming, on behalf of Division 35, welcoming Joe Shepard to JPL.
Thanks very much, and actually I've had a long association with Division 35 and JPL, and it's actually nice to be back here speaking to you, although I prefer to have a different topic. But what this talk is all about is, I call this sort of Fukushima for scientists and engineers. So you've heard a lot of things on the news, and there's been a lot of so-called experts that get up and talk about things. And as I watch that stuff, and my wife watched me getting disgusted, she said, well, why don't you do something about that? I said, you know something about it, why don't you stand up and talk about it? And so that's one of the reasons why I'm here. And there's a couple of purposes in this, and one is to give you kind of an understanding of the reactor systems and how they're supposed to function, and then an understanding of what I know about could have been wrong with a little bit of speculation, but actually I don't have any secret knowledge. And so all I'm going to tell you is things that I learned off of, as they say nowadays, scraping the web and talking to a few people who are inside the nuclear industry and my 30 years of experience in thinking about nuclear reactor safety, which started when really even before that, when I was a graduate student who worked at Oak Ridge. So here we go. So there's a number of nuclear power plants in Japan. and they get about 30% of their electricity from that. They're heavily dependent on it. And right here on the coast are the plants that were affected the most by the earthquake and tsunami. And the plant we're going to be interested in is this one particular plant, which is Fukushima #1, or Dai-Ichi, and this actually contains 6 reactors. And so there's a bit of an economy of scale when you build nuclear power plants. At least it was a perceived economy of scale. And so you often put a large number of reactors together and make a plant, but it really consists of actually 6 units. We can see 4 of the units here, and it's #1, the oldest one, and then 2, 3, and 4. 2 of 3 and 4 have a lot more in common, and 1 is a little bit smaller, but they're basically the same design. It's a question of scale. This building, these sets of buildings here are the turbine buildings, so these actually house the turbines and the generators, and there's a number of auxiliary buildings, large stacks to carry off the material. So the plants were designed in the late 50s and 60s and were built during the 60s, and the first one started and had its low power startup in 1970. It's been running since then. The other ones have startups that were a little bit later on in time. So these plants have been here for some time. The first plants were built by GE. This is an audience that of scientists and engineers who probably don't need this little bit of discussion, but just to remind ourselves what we're doing here is these are thermal power reactors, and so we have slow neutrons. The neutrons are moderated by water, and the neutrons have a large cross-section when they're slow for fission, and that means we make somewhere between 2 and 3 neutrons, a number of fission products, which are the things that cause us the greatest concern when we have a problem like we do today, plus about 200 MeV of energy, which is turned into thermal power in the form of high pressure, high temperature steam, which then produces electricity. And the thing that's, of course, greatly attractive about this is 1 ton of the isotope 235 will produce a gigawatt of electricity for 1 year. So that's what we're talking about here. And here's the actual internals. And so there's each one of these reactors and associated systems consists of the following. It has a pressure vessel, it has some fuel inside of here, and it has a very large amount of water. This is a boiling water reactor. And they all boil water, but in particular this one boils the water directly inside the reactor. And there's up here on the top are what are called the dryers and separators, so that only the steam goes into the turbines, and then the water, after it goes through the turbines and spins the turbines and makes electricity, gets condensed by the condenser, and 70% of the energy actually goes in the ocean. These plants are on the order of 30 to 32% efficient, and so there's an enormous amount of water that's being circulated in here, 6 tons a second. Basically comes out of the pumps at about 180 degrees C, gets preheated, goes in the core, goes down, around, up, and out. So that's what we're doing. So we're doing that day in, day out. The capacity factors on nuclear plants are up on the order of 90 to 95% nowadays, and so these will run for probably a period of up to a year and a half before they have to go in and change out some of the fuel. So a lot of the events that we're going to be talking about have to do with how this structure and the associated components did or didn't work, and so you have to put the pressure vessel inside of the structure in order to both protect it from external events and also internal events. And so the structure is a large reinforced concrete building. Here's our pressure vessel. It's got the fuel rods inside of it. In addition, in this particular reactor, is so-called Mark I. That's because that was a designation that GE gave it. This was their first design. In this particular reactor, some of the spent fuel winds up residing in a pool with a biological shielded water on it, which is up at the level of the upper head, because they can take the fuel in and out of the reactor underwater and move it back and forth to the fuel pool, and then let it cool down before they have to move it to more permanent storage. One of the things you want to do is you want to make sure if something goes wrong, that you're able to capture the fission products, and there's multiple layers to do that. One of the most important layers is the containment structure. And the first containment structure is there's zirconium around the fuel rods, and they're actually pins, and there's thousands of these pins. They're grouped together in assemblies of about 64 pins each, and then you have several hundred of those assemblies. So that's the first barrier to the fission products, and it's all inside of the reactor pressure vessel. The reactor pressure vessel is connected to high pressure piping that and pumps, and then the whole thing is inside of the building. Here's what the assemblies look like, and so here you can see the set of pins, and they're about half an inch in diameter and on the order of 12 feet long, and they're full of little pellets of uranium dioxide, which is a mixture of the common isotope 238 and slightly enriched with 235, probably about 3.5% for this reactor. There's a lot of uranium inside of this reactor. There's probably 68 tons in the little one and 94 tons in the two bigger ones. And in addition, there's a large amount of material that's used to control the reaction, boron carbide. And we talk about its control rods. There are rods down at the bottom, but they're actually blades here. So here's the containment structure. This is a reactor that was built in the United States some time ago, but still operating. It's called Browns Ferry, and it's in Alabama. And this is the sphere. So the reactor pressure vessel is inside of here. You can imagine this reactor pressure vessel, which is about 20 meters high and 5 meters in diameter, sitting down inside of this structure. This structure itself is a pressure vessel that holds a little bit less pressure. So the reactor pressure vessel itself is holding 70 atmospheres. This is designed for 4. We probably can go up to 8 and fail at some point beyond that. In addition to this sphere and this cylinder, there's a head that goes on the top, and that allows it to hold pressure. There's a number of hatches and seal it up. There's a lot of piping that goes in and out, and then there's a large torus down here in the bottom. You put a pool of water in that torus, and that plays an important role when you have an accident in terms of removing fission products and heat. The whole thing is embedded in a very large amount of concrete, and that pressure vessel that we saw, that very substantial looking structure, doesn't even show up here. It's just a little thin line, and then there's all this concrete around it. And there's a whole lot of equipment and passageways that's not being shown here. We're showing the skeleton of what we have. And so this is called the containment vessel, or the primary containment. And then here the cross-section of the torus. And then there's vent pipes that connect the sphere to the torus. And the notion is that this water will provide some suppression of any steam transients that get created. And then this volume will accommodate some of that. And then you have things like sprays in there to reduce the pressure. So when the reactor is operating, it's full of these assemblies, and but this is the case when it's not operating. This is the refueling bay. You want to remember what this looks like, because this plays an important role in the accident. And this is actually the head. This is probably the head of the primary containment vessel. The reactor vessel head is a little bit smaller, and there's a very large crane here. And this is what you can see if you look down. So there's a very large amount of water here, and you're seeing what's called the Cherenkov radiation, because you have very high energy particles, a lot of gammas and betas, and those are generating this characteristic blue glow. And here's the process of moving the fuel rods in and out and over to the spent fuel pool back. So now the thing about the PWR is that it doesn't have a secondary heat exchanger. So the PWR, which is the other kind of reactor that was developed by Admiral Rickover in the nuclear navy, was developed by Westinghouse. The PWR has a secondary heat exchanger. Actually, usually has several secondary heat exchangers. And the PWR is quite a complex design. And the PWR was actually developed as a civilian effort that came out of Argonne National Lab and Idaho National Laboratories. And the idea was to develop something that was simpler, a little easier to control. You didn't have to worry about having all the pressurizers and secondary heat exchangers and so on. But the drawback is that water that circulates inside the core also goes light into the turbines, and so this water picks up radioisotopes, and any impurities in the water can be activated. So it is radioactively hot, and that's why you have this large amount of shielding around the turbine. You've also heard discussions perhaps on the news about the water in the basement of this room being highly radioactive, and the water in the basement probably came from the 138 tons of water that's circulating through the system that comes directly into here. So how do we control the reactor? So the reactors are systems that you'd like to have negative feedback stability on. It's an obvious thing that you want to have when something has extremely large amount of energy. You would like when you have a small perturbation that it says, oh, okay, I will adjust myself and I will reduce the power, or I will increase the power and come back to the operating condition. And one of the ways that you do that is you design that into the reactor, so that's an engineering feature that has to do with the neutronics and the thermal hydraulics of the cooling. But the other thing you can do is you can actively put in these control blades, and here's the control blades, these cruciform shapes, and there are control rods here, and they're pushing it up into the into the core, and there's a very large number of penetrations in the bottom of the reactor that come in from the bottom. And so nuclear engineers sometimes like to say that the BWR is an unnatural creature because the control is accomplished from the bottom rather than the top, as it is in the PWR. But if you put them in through the bottom, then it's very easy to take the head off of the top and exchange the fuel. So one of the things they pay a lot of attention to is making sure that they have systems to insert the control rods and the reactivity controlling boron carbide blades very quickly in case of something that happens like a large earthquake. There's a huge amount of machinery both in the turbine building and in the reactor building itself. For example, pumps that can pump this massive amount of water around. In this case, this is a pump we'll be talking about a little later on. It's not driven by electricity, it's driven by steam, and it can actually move 138 tons an hour, which is not as much as 6 tons a second, but it's substantial. Here's a high-pressure coolant injection pump. These are safety features, and so these last two pumps that I showed are actually not ones that are ordinarily used. These are not the feedwater pumps, but they're actually safety features. And we have additional safety features, and one of the things that's very important is it takes a substantial amount of electric power to run the instrumentation, to run the pumps and the valves, and you often worry about things happening like there's an upset in the grid. And so surprisingly enough, even though you're generating hundreds and hundreds of megawatts of electric power, you're relying on the grid itself for the stability. You don't want to rely on your own ability to make that electric power to run your equipment. And so what you have is you have backup diesel generators. And you don't just have one backup diesel generator, but you have multiple backup diesel generators. In this case, in this plant, probably in between the 6 plants, it's something like 13 backup diesel generators. And they're enormous things. They generate somewhere between 2 and 6 megawatts per set. So finally, if things really go south, so the thing about backup generators, if you have experience with those, it's like starting a lawnmower after you leave it out in the shed all winter. You're probably going to have to go drain the gas and make sure it actually will start. And so they spend a lot of time doing that, but still, nevertheless, when you have equipment that runs intermittently, there's always issues about reliability, and so they also incorporate a very large supply of batteries and the inverters, and so they can run certain critical parts, but it's really only key instruments and controls. You obviously can't run those big pumps off of them. That's one of the issues here. So finally, here's what some of the structures look like. These structures are enormous engineering structures. This is inside of the torus. This is in the torus room itself, and this is one of the vents that comes in. And these are the number of pipes that are fed steam from the reactor, and you can imagine that this would be about half full of water when it's actually operating. So, very complex control systems. This is one of the things that was criticized after 3 Mile Islands. There's a lot of concern about human factors, making sure that the operators can actually understand what is taking place in the reactor and then perform the appropriate actions. And so there's been efforts on that over the years, but these reactors were built in the 1960s, and so some of the controls that you can see look exactly like you would expect to see in something built in the 1960s. So some of you who have been around for a little while, like me, have probably operated pieces of machinery like that up here. So here we are, normal operation. So here's what's happening prior to the earthquake on March 11th. We're circulating water with one of these enormous pumps. It's going in, goes to the downcomer, turns around, comes back up, goes to the core. It starts boiling somewhere up here in the core. We want to have the fraction of vapor be about less than 50%. It gets dried out then, superheated, becomes just steam, very high quality steam comes through. The turbine spins the turbine, goes down into the condenser. An enormous amount of river water that's running through here to dump all of that excess energy that we can't use, and then it comes back and gets pumped by a very large feedwater pump, actually a series of feedwater pumps back into the reactor. Everything's happening just fine, and all of a sudden it says, okay, now stop. Any number of reasons why this could stop. It could be some kind of an upset in the feedwater. You're monitoring a lot of different conditions. So you imagine it's a very complex engineering system. There are many, many things that could trigger a shutdown, and it doesn't have to be a earthquake. An example of 3 Mile Island, there was some kind of an upset of the feedwater. It's not really clear to this day what that upset was, but that triggered the whole event then. So once you get an upset, then what do? Well, immediately you push in the control rods, and those boron carbide blades go up into the reactor core, and you stop almost all of the heat from coming out. And that's an important point. It turns out you can't completely eliminate all of it. All what you've done is really try to intercept all of the neutrons, and you spoil the whole chain reaction that's taking place, but you're left then with a problem that it's still quite hot, and also it turns out there is some spontaneous radioactive decay you have to take care of. And so you still have to be pumping water around here, and you continue to do that, but you bypass yourself around the turbine, and you close this main steam isolation valve, and you run through your condenser in the usual way, and you also have to be running the water in from the ocean. So this then goes on for some time. You have to do this for a period of weeks to get this thing cooled down to the point where you get to actually what they call cold shutdown, and you can pull the head off of it and you can start working on it. So now, what's the concern? The concern here is that what we're doing is we're burning U-235. We burn the U-235 in sort of the loose chemical sense, and we have these interactions with neutrons. We're making a lot of stuff that we would really rather not have, and those are the fission products. And so we're going to burn, we don't burn all of the U-235. Some of it's going to be left after the fuel spends about 3 years in the reactor. And in addition, we're going to take some of that 238 that we started out with, and we actually turn that into plutonium. And some of that plutonium will decay, but we have plutonium left. And so this happens in all reactors, so you inevitably wind up with plutonium. Some of that plutonium is 238, which some of you might be familiar with because it's used in radio stuff for electric generators. And so we have a problem having enough of it, but they don't have a problem having enough of it here. So, and then there's a lot of things that you really don't want to get out in the environment. In particular, you've heard a lot of focus on things like cesium-137 and iodine. So it's a lot per core. 38 kilograms is an enormous amount of radioactivity because the decay rate, for example, in the iodine is 8 days, and the cesium is 30 years, and so it's pretty intensely radioactive. So, problem is that some of these materials are undergoing spontaneous decay. Fission products are the juvenile delinquent of the atomic world. They're unstable. They have too many neutrons. They have to get rid of the neutrons. They go beta decay. And when they do that, they release about one MeV of energy per each decay. And there's a decay chain. The decay chain might be, say, 7 nuclide long before it gets to a stable compound and it stops. So it's not going to stop till it gets to stability. That can take, in some cases, tens or thousands of years, but for many of the fission products, they decay very quickly, and all that decay comes with energy, and what you wind up with is, as soon as you shut down the power to the reactor by entering the control rods, you're still left with this decay heat, and it's about 7% of the full thermal power. So in Unit 1, we were making 1,380 megawatts of thermal power, and we're going to be left with, even with it as shut down as we possibly can, about 90 megawatts right at that point. And then very quickly, because a lot of those isotopes have very short half-lives, then the activity is going to decrease, but then that trails off. This is something like 10 to the minus 2/5, and we wind up with even dealing after 8 hours with 10 megawatts. And here we are 400 hours after we've done that, and this is in units 2 and 3, which have an even larger energy release when they're operating, and you're still having to deal with something on the order of 10 megawatts. So 10 megawatts is a lot of energy to get rid of. So you cannot just imagine that's going to go away. So that's the thing that you have to do with how to get rid of this heat. So what do you have to do to get rid of the heat? Well, water. So you have to put in water. And you put in cold water, and you've been hearing about that on the news, you've been listening to it, and the cold water comes in, and what does the cold water do? Well, unless you can put in a lot of cold water, and that's what all these systems are designed to do, this high-pressure coolant injection system, this low-pressure coolant injection system, the main feed water pumps, even this reactor containment isolation system, the steam-driven pump, they all put in, you can see many 100 or more tons here, 1,000 tons per hour, and here's what we're able to do with the little backup pumps there. So what does it do? It all turns to steam, and then it runs out into the building, and it condenses, and goes down into the basements. So you have to figure out how to get rid of this. I mean, it's sort of an inexorable thing. There's really not much you can do about that. So what do? You worry about that a lot. You say, okay, I'm going to put all kinds of systems in. First of all, the control rods don't go in. I'm going to have some boron poison I can flow in there and get rid of it. If the main cooling system fails, I'm going to have 1, 2, 3, 4, 5 different kinds of things that I can do. So that is fantastic. You have a lot of backup systems there, and it winds up being something with a lot of duplicate things, and there's whole trains of diesel generators and all that stuff. But it turns out that only one of these things can work without electricity, and that's this one right here. So none of these other beautifully engineered systems, the removal of heat from the suppression pool, the injection of water at high pressure or low pressure, all of those things require very substantial amounts of electricity. And then you're left with this one device here, a steam-driven pump. So, okay, so now you are all experts on nuclear power and nuclear reactor safety, and now we're going to walk through the accident. So, here we are, March the 10th. This is what the plant used to look like. There's the breakwater here. Here are the intakes for the main the cooling. This is the feed water, but this is what cools the feed water in the condensers. And the exit is somewhere over here. And turbine buildings and reactors. So we get a huge earthquake, and the shaking goes on for a very long time. And the shaking at Fukushima looks something like this, and it's about twice as large. These units, a gal is a centimeter per second squared, and so you get about twice as much shaking as the design. And immediately the electrical grid fails. When the electrical grid fails and the plant shakes that much, you have multiple sensors that are telling you there's something very bad happening here, we are shutting this plant down. And so at that point, the reactor shutdown was initiated, and one of the causes of concern, of course, is then there's a very long series of aftershocks. And today, this morning, late at night in Japan, they had a very large aftershock takes place. And some of these aftershocks probably played a role in the accident, although that's not clear yet. So now, here's some important things about this reactor. When it's running normally, one of the things that you worry about is you worry about getting something happening in the reactor that produces explosive gases. And so what you do is you actually fill up this primary containment for this reactor only, this Mark I, with nitrogen. In fact, it's been on the news because they decided to go back and refill Unit 1 with nitrogen. Well, what's the point of that? Well, we'll come back to that. But the point really is that if you make some combustible gases, you want enough nitrogen to be in here so that, say, the amount of oxygen is less than 2%, so the atmosphere is effectively inert. So here you are, you're running, here's your core, it's making heat. You got water coming in from the condenser, steam's going out. And we're cooling this. We've shut the thing down, and it's safe at this point. And the engineers are shook up because you had an enormous earthquake, but the gauges seem to indicate everything is fine. And about 30 or 40 minutes later, here comes this tremendous tsunami, or actually probably a series of waves. And this is actually a picture of one of the waves being reflected back out. So the breakwater is here, and this is the wave actually coming back out from shore after it's reflected. So it's like any kind of a wave that carries a certain amount of energy and momentum, and it's not just going to stop. A lot of it ran up into the land. It's not quite clear how far it went, but it certainly overran the breakwater. It was substantially higher than it had been designed for, which was 6 meters, and ran up into this area. And now at that point, the other thing that happened was the earth has moved really substantially, in some cases up to 4 meters. So we're right here. So it's that big arrow. So Fukushima Dai-Ichi is somewhere down here. And the land dropped 1 meter. So this is just an enormous series of external events. And at that point, what happened was all 13 backup generators failed. Now, some of those backup generators were brought online relatively quickly, and they brought in some additional portable generators, but the generators that were most important, which were units 1, 2, 3, and 4, were failed. In fact, they were failed in such a way that they couldn't be recovered. And one of the problems was this enormous amount of damage that was done by the combination of the earthquake and the tsunami, and this is a lot of debris that was up on the dock. So here's the accident progression. The Japanese have been excoriated a little bit in the press for not being forthcoming, but actually if you go and you look on the website, it's not clear how accurate the information is, but they publish things right down to the minute when various things happen. So if you go to the Japanese Nuclear Safety Agency, you can get a lot of this information, which is what I've done. Some of the information seems to be a little bit anecdotal, but here we are. The reactor shut down when the earthquake happened at at 1446, then we had the shutdown, we're shut down, and then the tsunami reaches, and then after the tsunami reaches, then we find out that we suddenly are in a situation where we have to rely on batteries, and that is a very serious thing, having to rely on batteries, because now you can't run any of these systems except for just the one heat removal system that you have. So the way that this works in Japan is that you have to declare an emergency, and you actually have to tell the Prime Minister, and so you'll see all along here they're declaring emergencies, and what they did then was turn on these backup systems, and there are two kinds of backup systems. In the old reactor, what they had was a natural convection loop, and they would take the hot steam out of the reactor, and they had a large pool of water. They'd use that as a heat sink. It's a total loss mechanism, and then the water circulates back down in the reactor and just sits there, and what are you doing? You're boiling off this water. What do you do in the other plants? Well, you have this reactor coolant isolation system, and you take the steam, and instead of running it through a passive heat exchanger, you turn a turbine. The turbine, then the exhaust from that goes down into the suppression pool. The suppression pool is large. There's a lot of tons of water in there, several thousand. So that's not probably not large enough. And then the water gets pulled up and comes back in here, and so now we have again, a total loss system. Well, so you're all engineers and scientists, and so you can tell me what's wrong with this. Right? So what's wrong with this? It can only go on for so long. You're not taking the heat out. You're still not, the heat's not going anywhere. Basically, it's like a thermodynamics problem where you say, well, consider an adiabatic box with a heat source inside. So at some point, also, you're going to start boiling the water, and you're going to start pressurizing the primary container, which is still supposed to be full of nitrogen unless somehow it started to leak out and you had the earthquake. So all this is very alarming, and the Japanese had been through a very serious accident in 1999 at a reprocessing plant in which there was a lot of miscommunication. It was very badly handled, and as a consequence, they constructed this system of notifications. And so this is what's supposed to happen. And so there's a whole lot of people involved. Societies are complex, you know, and you're going to have to tell a lot of people that things are going on. You're going to have to figure out how to deal with everybody, self-defense forces, fire department, police department. And they said, well, you know, these things are such a challenge to our society that at the end of the day, we're going to pick it all upstairs to the Prime Minister. So that's why you see the Prime Minister on television. And as I say when I give this talk, it's a good thing he's a physicist. So he can evaluate all of these things he's being told. And hopefully he has a whole lot of other people that are giving advice about that, which I'm sure that he is. So this is the system they have. And so now TEPCO's on the phone to the ministry. The ministry's on the phone to the Prime Minister, and they're saying, here's the deal. So what's happening is we're pushing the steam into these suppression pools, or we're boiling the water off of the pool that we're using to condense it, and we've got to the point now where we can't cool it anymore. And what are we going to do? Well, one of the things that you don't want to do is you don't want to fail this reactor pressure vessel. So that's one of your lines of defense. And you also don't want to fail the other line of defense, which is this outer containment vessel. So in order to keep the pressure from going up, you have to get rid of some of that steam. And so when you get rid of some of that steam, it's the same thing that happens when you take the top off of the pressure cooker. A lot of the steam flashes and you start losing inventory. So you start uncovering the core. It's more complicated than that in the PWR because the PWR has a lot of steam in it anyway, but you just have a lot more steam and you have a large portion of the core that's uncovered. So now the really bad thing begins to happen. And this is where I came in. It's not that I did the bad thing, but this is the part that I spent a lot of time thinking about when I was in Sandia Labs. What happens is if you get the core too hot, if you remember you've got all these little pellets that the size of your fingertip, tens of thousands of these pellets of uranium dioxide, and they're inside of this zirconium rod which has a cladding which is only 1 millimeter thick. And if you get that too hot, it turns out all those fission products, a lot of them are gases, so the krypton and the xenon and so on are gases, and they're at high pressure, and they're going to cause the cladding to balloon and to rupture, and they're going to release the fission products. And at the same time, the other thing that's happening is that the zirconium is getting hot, you've got steam in there, and the steam will oxidize the zirconium, and it makes hydrogen. So you now you've gone from a worse situation to a really terrible situation. So you've still got nitrogen in here, and so you say, well, thank God, I filled the whole thing up with nitrogen. But then the reactor pressure starts going up. And so here we are, and here we are on Saturday. So the tsunami happened and the earthquake happened on Friday, and now here it is Saturday, and they're measuring the pressure, and the estimates are still working, and here they are at 600 kilopascals, and now they're 800 kilopascals. You remember what I said? This is inside the primary containment. It's designed for 400. You start to worry about it failing when it gets to 800. It probably will definitely fail at 1,000. And so here you are getting ready to fail. All right, so what do? You say, well, what we're going to do, we're just going to let some of that steam out of the primary containment. Now, that's something that people have talked about a lot with these reactors. The problem with it is this, that what you're going to do is you're going to release fission products directly in the environment. You hope that some of those fission products are going to go through the suppression pool and get scrubbed out, but the fact of the matter is a number of those will probably just go right on through and out in the environment. The other problem is, where is that going to go? Where are you going to put this material? Because in fact, it's not just fission products, but it's nitrogen and hydrogen and steam. And so now you may be dumping nitrogen, hydrogen, steam, and fission products into air. And this stuff is at pretty high temperatures, and you have all kinds of electrical switchgear and sources of ignition. And so the fact of the matter is, what happens is that you wind up with an explosion inside the reactor building when you vent the steam from the primary system. And that's exactly what happened here about 3 o'clock in the afternoon, 3:30 in the afternoon on Saturday. So that's Unit 1. Unit 1 was the smallest unit, but it also had the oldest heat removal system that was completely passive, and apparently they just boiled that pool off and very quickly got into the situation. So this is what we had. So we had to vent directly out of the primary containment, and we had to vent into the reactor building, and this reactor building is actually designed to fail gracefully. Now, it didn't fail gracefully. You saw the pictures. The first one failed more or less gracefully, if such a thing is possible. But that means you have a very low overpressure failure for the panels that are on the top here. But one of the things that you're going to have to do is you're then going to have to deal with resulting debris and damage up here, because this is also where you have the fuel. So, here's the explosion. It was pretty horrifying to see this if you're involved in if you're engineering, and it's the kind of thing that just absolutely should not happen. And if I can get this thing to talk to the web and pull this up, then you can see what this looks like. And so here's the actually where it'll play this back here in a minute. So you can see this enormous cloud here. So what is that cloud? Well, that cloud is probably a lot of pulverized concrete and steam, because the panels, even though they're blowout panels, the panels are made out of, there you go. And you can see there's a tremendous jet that went up in the air. So it was just an absolutely heartbreaking thing to see that happen, and then to think about the fact that there were all these fission products inside this cloud, which are now off drifting to the northwest, and we'll see where they wind up with a little later on. So that's what happened there. And now, so what blew up? Well, what blew up was this area right here on the top, and all of this superstructure you can see. That's all of this superstructure that was designed to hold on these panels. And so, in some sense, you say, well, the safety system worked. We blew off the panels, and hopefully we didn't damage a couple of key things we're going to need to recover this accident, which is the crane. We didn't damage the fuel pool, and we didn't damage the reactor, which is way down inside of this, underneath this concrete shield, and the upper part of the retaining vessel. But we actually don't know. We don't know what the condition of that is. So, okay. So now what are you thinking about? Well, there's still other things that can happen. When the reactor is running, the inside, this is a cross-section of the fuel pin. So this is the center line. This is about a ½ an inch out here. This is a little bit of zirconium. In this case, it's less than a millimeter. Here's the gap, which is full of helium to start out with, but you've got some fission products in there and some oxygen and nitrogen, and you've got a very strong temperature gradient. And this is how it's supposed to work. So this is what you're going to have when you've got water flowing by here and you're extracting the you can imagine, all of you who've done the transfer calculations will know what's going to happen if I insulate this battery, and then basically we're going to float up to a common temperature, and then that temperature is going to go up and up and up, and until we balance the internal heat generation with the heat losses, and what you go is from a situation where you start to oxidize the zircaloy, and you make hydrogen, and then you start to actually dissolve melt the zircaloy, and then you dissolve the zircaloy in the uranium, and then you finally melt the boron carbide, and then finally, at the end of the day, you could actually get up to these kinds of temperatures. You could melt the uranium dioxide, and that forms eutectic with this chromium, and it drops down into the bottom of the core. This is the kind of thing that can happen when you just have a ballooning and rupture of the clad, but you can also get a lot of fractures in there, and that's how the fission products get released into the water, and that's why there's so much fission products. So hydrogen comes out quickly, and of course it accelerates with temperature, and it releases energy. So it's a self-accelerating reaction. When you're basically burning metal, you can burn metals in steam, and so this releases a substantial amount of energy, and that contributes to the process running away. Where does all that hydrogen go? Well, the hydrogen goes into containment. If you go into the primary containment on the Mark I, you can really fill it up and you can get a lot of hydrogen. If you have all the metal and water react, you can fill it up with 70% hydrogen. But in fact, we're not going to fill up the containment. So what we've done is after we fill up the containment, then we're going to vent it out into this reactor bay, which is about 1 million cubic feet. And so the concentration is not quite so high, but the concentration is extremely high. And what happens? Of course, it burns, and when it burns, we're going to release energy. We release about 120 megajoules per kilogram. We can make a very large number of kilograms of hydrogen from oxidizing the zircaloy. And if we measure what the peak pressures are, we can easily exceed. If you remember, the pressure, the failure pressure that I showed was only about 5 psi, so it's way down here. And so any kind of combustion that takes place will cause that structure to fail, and we have a pretty substantial understanding of the conditions under which the combustion can take place, and some prototypic tests that were done in Nevada showed that we could get combustion with up to 30% steam, so you can't really take necessarily credit for all that steam. What does happen is if you have a very low concentration of hydrogen, that you get a buoyancy effect, and these are some pictures of some planes that were taken with high-speed video in my lab, and here's a picture that shows what you have with about 10% hydrogen, and you can see that you have this very corrugated, convoluted surface because it's naturally unstable. And then if you go down to about 5% hydrogen, what you have is a substantial effect of buoyancy, and you create a vortex inside of here, and it drags the plane up to the top. Still get very substantial overpressures. So here we are, failed the secondary containment, but even worse things can happen, which is that low-speed planes, which are only going a few tens of meters a second, in those pictures I showed you, if you have enough hydrogen concentration and you have a small enough amount of steam, then you can actually get detonations with very high-speed combustion, and this very high-speed combustion can move at 1,600 to 2,000 meters a second, and now then this produces an impulsive type of load and produces a much more destructive event. So, next unit, so unit 3. So here we are in unit 3, and one of the things that's happening is we're running on batteries. We still haven't been able to recover, so now we're into Sunday. So this all started on Friday afternoon, goes into Sunday, and now we find that successively the batteries are running out, and in addition, this reactor core isolation system fails. And so now we're beginning to wonder what's going to be happening. It's still working in Unit 2, so Unit 3 is failing, Unit 2 is still working. And here we get now, here we are in about 11 o'clock in the morning, and Unit 3 undergoes the same kind of event, except that this event was really quite astonishing in its intensity. And you can see here where these towers are about 100 meters high, and so this is not the ultimate height of the cloud. I tried to estimate that, but maybe we went up 500 to 700 meters, just the visible part of it. And that's extremely energetic. So,
what are those towers?
What's that? Those towers? So these towers are the so-called, there's the top of the cloud, you can see. These towers are what are called the stacks, and what they do is they take filtered air and out of the reactor buildings and the turbine buildings, and see that little flash of flame right there? It's an enormous cloud, and then you can see bits of stuff that come falling back down. It's just it's unbelievable. So what those stacks do is that you have to ventilate the buildings, and you have to filter out the particulates, and you have to try to trap out any of the radionuclides, and so you run it through some HEPA filters and some activated carbon, and then you try to push it as far up in the atmosphere as you can so it doesn't come down in the local vicinity. So that's what the stacks are for. This is the result. It's pretty horrific. So what it did in this case was, now you can see that superstructure is not left at all. The superstructure, in fact, has fallen into the reactor, and what's an even greater concern is it's fallen into where those spent fuel pools are. So now we have two reactors that have destroyed the superstructure. This reactor number 3 had this enormous explosion that's heard 50 kilometers away. And now what's next? Well, what's next is we're not done yet, because reactor 2 is still sitting there. And what happens is that we successively, very quickly have events in reactor 2 and reactor 4. It's really not clear what happens in reactor 2, but apparently there's something that was not good. There was an explosive sound near the torus. And then reactor 4, now reactor 4 doesn't have any fuel in it, so what's going on there? Well, it doesn't have any fuel in it, but it has about 1,000 fuel assemblies sitting in the water in the spent fuel pool, because they're working on reactor 4. They took the assemblies out so they could go in and work on what's called the shroud. And they've been busy working on that. They have to store the fuel somewhere, and so that pool is quite full of fuel, and that fuel was taken out in November, and so it still has a substantial amount of decay heat, and so there's a concern about what's going on there. So what may have happened is that the water may have boiled off of the pool to the point where we exposed the cladding. We're no longer, do some rough mass energy balance calculations, probably take about a day. We're no longer cooling the rods, and they start generating hydrogen with the steam that's coming off the pool underneath that's boiling. You make hydrogen, the hydrogen starts to burn, so you have a fire. So this is a very bad thing to have, of course. And then, in addition to that, you seem to generate a lot of hydrogen, which gets into the reactor building and has an explosion. The upshot of all this is that it is severely damaged reactor 4. So here was that for reactor 3. You can see how a lot of the material has just been completely torn off of here from that enormous explosion. But here's reactor 4 now, and reactor 4 has a very large amount of damage into it also, so it had both a fire and an explosion. And you can see here, for example, into the building, and this is a piece of the crane, and you can see all of the panels have been torn off and the roof is collapsed. So this is looking down on unit 3 again. Here's looking at unit 4, and here's what the real concern is: the spent fuel pools is this unit 4, which has the 1,330 irradiated fuel assemblies, and the last additions was probably in November the 10th, when they took the entire core out. The entire core out is about 500 assemblies in units 2, 3, and 4. So very large amount of decay heat there, and that's why those fuels have to be kept cool. And what's going on in those pools? Well, the pools are here, roughly speaking, and down at the bottom there's about 3 or 4 meters of these fuel rod assemblies. They're put into racks. The racks are separated by it's called Boraflex. It's a polydimethyl siloxane, which has some boron in it, which is a super absorber of neutrons, and then there's a whole lot of water on top of it as a biological shield. And what's happening is this is sitting here boiling, because ordinarily what you have to do is you have to run a heat removal system. So you got a heat exchanger running, and you're pulling out all that heat. So you've got the 10 megawatts in this pool, just like you do in the reactor. Because the reactor itself is hot. You can figure out what's going to happen there, and it's going to be something bad. This is an example of what can happen if you remove the water, and this shows that after you've drained the pool out, that you'll start to have a self-accelerating reaction, and you'll go up very high in temperature. And if you remember this number, 1200 degrees, that's when you start to make the hydrogen. So there was a very substantial fire there, and so now this building has exploded and burned down. And so here we wind up with 1, 2, 3, 4, and 2. The building looks okay. In fact, inside of it is extensively damaged. So they spent a lot of time trying to put enough water into the pools to try to keep them cool. The solution that they had additional fires inside of that smoke and fission products. And the final solution they came up with is these specialty concrete pumping trucks. And so there's a stroke up here on the top. And what they're doing is they're running fire line coming from a pool where they have some temporary storage. They started out with seawater, they went to fresh water, and all the way up into the top is now pumping water into that pool. That pool holds about 1,000 tons. And so you need to be able to put the 1,000 tons in there, and then you need to replace whatever is evaporating because you don't have your heat renewal system working. You're trying to figure out how to do all this stuff under absolutely horrific conditions. So here you are in the control room in the dark, and it's radioactive, and you've got your suit on, and you're trying to piece together what has gone on here. Just absolutely horrible conditions to try to do engineering. And finally you get the lights back on, but even when you get the lights back on, you're standing around looking at a lot of blank screens and a lot of blank dials because a lot of this stuff is not working because you haven't turned power on the rest of the plant because you're worried about what's going to happen when you do that. Because you really need to go in there and inspect it, but it's way too radioactive and hot to do anything about that. Can't get in there. So here's the current situation. So the IAEA has been reading all the reports, and they have a lot of folks who think about this, as well as every other group that's interested in nuclear power, and they have been saying that the situation remains very serious now ever since the event took place. And so what do they mean by that? You read between the lines. You read between the lines, it means the situation is very precarious. You have failed all of your lines of defense. You have melted the core to some extent. You have ruptured the fuel rods. You're not sure if all the pressure vessels have integrity. You're not sure if the containment has integrity. The building has certainly failed. Your ventilation system doesn't work anymore. You're blind because a lot of your instrumentation doesn't work. And what you're basically doing is you're just trying to hang on by putting water in there to take out that decay heat. So you're struggling with not the second law, but just the first law of thermodynamics. So then the problem is, of course, is that this is a total loss cooling, right? You're pumping water in there and it's evaporating or it's running off into some catch area, hopefully, or worse, as it was for a while, running out to the ocean. So you've got to get out of that situation. You've eventually got to get your residual heat removal systems working. Or else you're going to have to give up on trying to ever recover those cores and just proceed to let them melt down. So here we are, and all the things in red are things that are severely damaged. All the things in yellow are things that are either we don't know anything about or we suspect they're damaged. And we've got a few good things that are blue. And right now what we're doing is we're pumping fresh water into all the pools, and we're injecting fresh water into all the reactors. But they're struggling now with what to do with all of that water. So it's making about 1,000 tons a day of water if you're pumping in 1,500 tons an hour to each one of those reactor pressure vessels, plus you have additional water. So that's what your storage requirements are. So you say, well, 1,000 tons a day, I can do that for a few days. Well, you might have to do this for years. So you look at the time it takes to recover all those systems, decontaminate the reactor, get all that stuff working, come up with a strategy. You might have to sit there and cool those things for an exceedingly long term. And so that's where the problem comes from. So I've been talking for quite a while and tried to give you some information about this. I didn't tell you everything that I know about it because I know that you'd all go to sleep. But I can take some questions and we can talk about other issues. Thank you.
That was a very interesting talk. On behalf of Division 35, we have a small gift for you. I do want to mention that we are taping this session, so like the next, this will be posted on Wire. It may go as far as YouTube, and so Joe.
Okay. Sure.
Yes. Oh, I'm going to run around Mike.
Yes, thank you. Did they have the option or the ability to vent the hydrogen directly to the atmosphere, perhaps through the vent stacks?
So what the Regulatory Commission told the operators in the United States in 1989, they looked at this. We had a very long exercise in the 1980s after 3 Mile about what to do with degraded core accidents, which is a technical term for these in these BWRs, especially the Mark ones. They said, hey, what you guys should do, you should put in a hard line that goes from the reactor and vents directly into the stacks. And I don't know whether they did that here or not. There are a number of vent lines. The problem is a lot of those vent lines are very low pressure vents, and if you vent 8 bars into those vents, you will fail them inside the reactor building. The other thing you like to do is you like to have some measure of filtration, so you would like to try to go through some of the filtration, although if you're going to vent very high enthalpy steam and high pressure nitrogen or hydrogen, you're probably going to have to give up some of that. And you're going to wind up pushing fission products right out in the atmosphere. What you're hoping is that the suppression pool is going to scrub out most of those. So I don't actually know what the situation was here. So that's a good question. That'll come out of the accident investigation. Yeah.
I was intrigued to find that you had also, in your background, had experience with dealing with the TWA Flight 800 catastrophe. And you and I exchanged some emails this week about that.
Yes.
And I'm still curious in probing your insights in dealing with catastrophic failure of complex systems. Are there any global insights that we should be watching for that are appearing in common in the way we approach these kinds of complex systems, which seem to be too big to fail, but then they do?
I think there are a lot of things about how we do this as a society, and specifically a subset of the society as engineers, how regulators and vendors and operators and analysts that work independently from organizations like the National Laboratory and universities. I think how we interact and how we have this discussion about safety, I think that's something that we really need to spend a lot of time thinking about, because one of the things that drives all these evaluations, and I can just to really impress you about how much I thought about this, I'll show you some other slides. So here's the last big evaluation that was done in this area, and this was called New Reg 1150, and it came out in the early 1990s. And this was an evaluation where they tried to go through and do systems analysis, do probabilistic risk assessment, and to do a lot of engineering analysis, and it was a large number of folks that were involved, people from national laboratories, people from the NRC, people from the vendors, GE, Hitachi, Westinghouse, and so on. And at the end of the day, they decided that indeed a big contributor to the risk was in fact these seismic events and this LSOP, which is exactly what we had, loss of offsite power. And in fact, we knew exquisitely, and one of the reasons why I was able to understand what's going on when I'm looking at this progression of things, these accidents were analyzed over and over again, and the conclusions that were reached always that, yes, this was a very bad thing. One should never have a long-term station blackout, and one should never have long-term loss of offsite power. And at the end of the day, we're going to put in these backup systems, and we're going to make, and one of the things about this is, and this is pointed out by the folks who evaluated this study, is they said, one of the problems here is that the dominant damage states will be driven by events that fail a multitude of systems, reducing the redundancies of common mode support system failure. Is exactly what happened here. So we know in complete detail why this happened, and actually it's not any surprise. But the problem is there were evaluations made about the probabilities of recovering the offsite power, recovering the generators, and those evaluations simply did not account for the circumstances that were here. And so we have to ask, okay, did we do it wrong in the sense that we didn't pick the right set of events? We should have really picked a 9. But I can tell you what the conversation should be like in the room. Oh, a 9. What's the probability of having an earthquake of that magnitude? And then a tsunami of that magnitude, all at the same time. What is the probability? And they've struggled with the probability of seismic failure. There's a lot of studies on it. It went on for 30 years. Morris Livermore Laboratories got involved, and there was a lot of controversy about that. In fact, in the New Reg 1150, there's 2 different sets of results. Depends on who predicted the seismicity. And at the end of the day, like a lot of these things that you look at in engineering systems that you all build and analyze, there's something called engineering judgment. And engineering judgment is the thing that comes in many of these areas. And the engineering judgments that were made, unfortunately, in this case, were not the correct ones for this event. So we're going to argue about event treats. We're going to argue about what the safety basis is. You're going to see a long, protracted discussion. That's what happened with 3 Mile Island, which was, by the way, a relatively innocuous and benign accident in comparison to this one. But we did soul searching for 15 years after that. So,
Thank you.
To what extent the catastrophe came due to poor management by TEPCO company and versus a design which did not anticipate?
I can't speak to that. I won't speak to that. I'm not there. I'm not involved in that American structure right now.
But the position is generators, all oil generators down there, water down.
Across, is it design or a maintenance?
Well,
Failure of all generators which could be moved out or covered?
yeah, so my experience is it's always very easy for us to look at what was done in the 1960s and 1970s and go back and say, ha, for crying out loud, why did you do it that way? But I can point to any number of aerospace systems that were designed the same way. And we all know that our thinking about these things has evolved in time. And so, you know, the question is now, really, is going to be, do you go back to these plants, which are now 30 and 40 years old? A number of these plants around the world are in a situation where they're going to ask for having their licenses extended. It's something that's economical. And now the question is we have as a society is, should we do that with this old plant that has features in there that now that we look at it with these new eyes and we look at it in terms of these accidents, we might say, yeah, you know, I don't think we should have done that. But how much is it going to cost them to pull all that stuff out of the base from the turbine motor? How much is it going to cost them to change the whole safety systems? At the end of the day, of course, these plants are a complete economic write-off anyway. They're gone, right? They're finished with this. It's pretty clear looking at it. But that's going to be the question for us. What's the trade-off in backfilling these plants, and where are we going to make the trade-offs in building new plants? I think that's a real substantive issue for us to grapple with as we move forward.
Joey, that
Okay.
Yeah.
You indicated that the cooling would have to go on for years before these are stabilized.
Yeah.
All right. Would you be willing to tell us the worst case scenario? Like there's more earthquakes, tsunamis, and they can't do the cooling? What is the worst
I think we
case?
can all imagine what's worst case. I don't want to go into that.
Okay, very good.